Hey everyone, we're back. We're going to do some more pre-calculus. Yay! And first of all, can you figure out what background I'm using here? What's this from? So let's see if you can figure that out. But we are going to look at today chapter 3.1, which is on exponential functions. Exponential functions, everyone's favorite. And so before we can do that, we actually need to review a few things that you probably all remember, but we just got to make sure we got them tight. So first of all, it's always good to remember square root of x is x to the 1/2. There we go. All right, cube root of x, of x is x to the 1/3. Fourth root, blah, 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 is blah, blah, blah. Right? Also, x to the -3 is the same thing as 1 over x cubed. And likewise, 1 over x to the -3 is equal to x cubed. When you move something from the denominator to the numerator, the only way you can do that is put a negative on its exponent. So if I do it from here to here, I put a negative, I multiply it, raise it to the -1 power, and that's going to move it up top, and it'll be a -1 times a -3, it'll come out positive. So if you have x squared over y cubed, well, that's the same as x squared y to the -3, right? The exponent, the function comes up here and its exponent changes sign from positive to negative or negative to positive. Either one, okay? Also, recall 2 divided by 3 is the same as, let's see, let's flip that over and we do multiplication. Right? When you divide, you flip the second thing over and you multiply. Okay, and likewise, let's see, we can do it the opposite way. 2 divided by 1/3. I could write this as 2 divided by 1/3. You flip it and multiply. Well, that's 2 times 3 over 1. That's 6. When a function down here, when you move it up to the numerator, it changes, it flips. And you could also write this as 2 over 3 to the -1, right? And what we say over here? That when we move something from the denominator to the numerator or numerator to the denominator, its exponent changes sign. So if I want to move this up here, I have to make that 3 to the +1 instead of 3 to the -1, which is 6. Always got to remember a fraction in the denominator, x over 2/7 is going to be the same as x times the reciprocal of that, equals 7x over 2, because you can multiply fractions straight across, right? So whenever we have these fractions down here in the numerator, down here in the denominator, we have to remember that we can flip them over and multiply them into the numerator. Now there's a few other things to recall. Cube root of x squared and x cubed squared. This is the same as x squared raised to the 1/3 power. And when you raise an exponent to an exponent, you multiply the exponents. And likewise here, I change this to an exponent. When you raise an exponent to an exponent, you multiply the exponents. Okay, so what is 5th root of x to the 7th? Well, that's going to be x to the 7th raised to the 5th. That's going to be 7 times 1/5 will be x to the 7/5. So this denominator is a root and the numerator is a power. When you see a fraction as an exponent, The denominator is a root, like x, like the fifth root, and the exponent is a power, like x to the seventh. Okay? We've got to remember those things. And lastly, what is x to the 0 power defined to be? It's defined to be 1. 2 to the 0 power is 1. 14 to the 0 power is 1. Squiggly line to the 0 power is 1. Anything to the 0 power is 1. Okay? It's very important. We need to remember that. So now, let's get to exponential functions. Exponential functions. So an example of an exponential function is y equals 2 to the x. And this has some special characteristics. So let's go x and y. So if I put in 1, 2 to the first power is 2. Look at that. When I put in 2, 2 to the second power is 4. If I put in 3, 2 to the third power is 8. Wow, this is getting big really quickly. 2 to the fourth power is 16. 5 will be 32, and so on and so on. So it starts to really take off. So here's 1, 2, 3, 4, 5. So this thing goes, it starts going ballistic really quickly. When I put in 0, it gets 1. So at 0, exponential functions always go through the point 0, 1. That's one of the clues that you can see that it's an exponential function, or that you can see it's shifted. If it goes through the point 0, 7, then it's probably been shifted up by 6 units. That's one way to help. Not always, but maybe that's a clue. But now let's go to smaller numbers. Let's go to numbers less than 1 and see what happens. Or no, less than 0, I mean, sorry. So if I put in -1, well, that'd be 2 to the -1. That'd be 1 over 2. That'd be 1/2. If I put in -2, that'd be 2 to the -2, which is 1 over 2 squared, which is 1/4. -3, 2 to the -3 would be 1 over 2 cubed. 2 cubed is 8, 1/8. So it's getting smaller and smaller and smaller, but it's never going to reach 0, right? I could put a number, 2 to the -100, and you're going to get a number, a 0 point something, but there's going to be numbers out here. It's not going to be 0, because this asymptotically approaches 0. So we have an asymptote here that the function always approaches 0 when you're going out here in this form. This one's going to approach 0 as x goes to -infinity. Okay? This is your classic exponential function. Approaches infinity when you go out really far negative. It goes through the point 0, 1, and on the positive side, when x is positive, it's going ballistic and it's taking off and it's getting bigger, 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 bigger. Okay? That's how it works. Now, let's look at a graph now. First of all, the general form of an equation of an exponential function is a times b to the x. Okay? And when x equals 0, what do we get here? Well, we'd get a times b to the 0. B to the 0 is 1, so we just get a. So when we graph, when x is equal to 0, this thing is going to go through the point A. So if there's a number there, it's going to go through the point A. It isn't uncommon for it to not have a number there, which means A is 1, and it goes through the point 0, 1. So I guess I kind of lied at you before when it said goes through the point 0, 1. Not always. But usually it'll be very common that there's no number here. Okay? And b is the number that we're squaring. In this graph, this is an example of b greater than 1. If b is equal to 1, 1 squared, 1 cubed, 1 to the fourth, it doesn't grow. Anytime b is bigger than 1, this thing is going to shoot off here and get bigger and bigger and bigger. But what happens if b is less than 1? What if we have f of x is equal to, we'll make a 1, and this is 1/2 to the x. So what happens when we take 1/2 and we raise it to an exponent? So let's see, for x, f of x, when x is 1, we get 1/2. Okay, when x is 2, we're going to get 1/4. When x is 3, we're going to get 1/2 times 1/2 times 1/2 will be 1/8. So if b is less than 0, it's going to be the other way around. It's going to go like that. b less than 1. Okay. Well, we're going to assume between 0 and 1. Because if a is negative, then it flip-flops between negative and positive, and it's not really a exponential function. It's something strange. So for b between 0 and 1, as x gets bigger, the function is going to get smaller because you're taking a fraction and raising it to an exponent. And anytime you take a fraction and raise it to an exponent, it's going to get smaller when the fraction is less than 1. If it's 9/8, well, this is a number bigger than 1. So this is in this category, right? But 8/9, it's close to 1, but it's still less than 1. And when you raise this to an exponent, it gets smaller and smaller as the exponent gets bigger and bigger. So that's important. Okay, so we could have either of these two cases. Now, we're going to give the name to these two cases. Oh, let's go regal purple. Oh, that's not regal purple. That's death black. Okay, so this one, where it's growing exponentially up, we will call exponential growth. Because as it's going upwards, it's growing. Hey, look at that. And the one where it decreases as x gets bigger, that's exponential decay. And there's two ways to tell exponential decay. So let me get rid of some stuff here. Here's some rules for exponential decay. So if f of x is equal to ab to the x, and a is greater than 0. Oh, sorry, let me write this again. It's really like this, kx. Because you could have it could be b to the 2x, or b to the 5x, or b to the 10x, or whatever. So if a is greater than 0, and k is greater than 0, then this is exponential growth. If, however, a is greater than 0, but k is less than 0, and this means exponential decay. Wait a minute. You just wrote one here like this. A times b to the x. And it looks like the number up here in front of x is 1, and that's greater than 0. Why isn't it exponential growth? Mark, you're a liar. No, I'm not. Because I can write this as, I'll get rid of the 1. 2, I can write as 2 to the minus 1 raised to the x. So I'm going to write this as 2 to the minus x, because when you raise an exponent to an exponent, you multiply. And, well, now, this is 2 to the minus 1 times x. K is -1. And k is negative means exponential decay. So you could have a fraction in here, and that's going to end up being decay. You could have f of x is equal to 2 times 3 to the negative 4x, exponential decay, because you got a negative k. If you had f of x, oops, kind of messy, equals 2 times 3 to the 1/4 x, what's that going to be? Well, it's still exponential decay because you still have a number here greater than 0. But it's not going to be very fast exponential decay, because if I put in 1 in for x, it makes the exponents 1/4. So it shrinks down the growth a lot, and it slows down the function a lot. But these are our general rules here that we want to keep track of. Okay? And you'll find those in the book, and it's really important. Here's our general equation for an exponential function. And we just need to look at it, and sometimes, like in this case, simplify it so we get it into the right form so we can tell whether it's exponential growth or exponential decay. Okay? So that's some good stuff. Now, sometimes the book is going to show f of x is equal to 2e to the 3x. And they're going to want to know, what's this, exponential decay and exponential growth? And you're going to say, what the heck is E? Well, E, I'll give you the definition, and I'll tell you what I think about it. E is equal to the limit, remember limits as x goes to infinity, of 1 plus 1 over x to the x. And you're probably thinking, what is this? And this is the definition somebody figured out. E is just a number, 2.71, blah, 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 blah. It's an irrational number because it cannot be represented as a ratio of two constants, of two numbers. So it's an irrational number. And it's used a lot in business, in science, exponential growth, interest-bearing accounts, you use e to the something. It's just a number that appears a lot in nature, and we're going to use it, but we're going to treat e as just a number, just like the number 4. It's just a number. It's a constant number that doesn't change. So here, what kind of growth is this? This is a number raised to the 3x. K is positive, so this is growth. Can I sketch a graph of that? Well, sure I could. When x is equal to 0, what does this function give us? In this case, it's going to give us a, 2. And since it's exponential growth, it's increasing on this side, and this side, it's exponentially decaying out to 0. So that's what this graph looks like. I'm not going to try to do the curve accurately or anything. If we wanted to, I could make a table of values. Oh, that'd be fun. And I put in 0 and we get 2. Oops. Put in 1 and we get 2 times e cubed. How do you do e cubed? You go to your calculator and you do e. If you have an x to the y button, well, you have an e button somewhere on your calculator. I bet you have a natural log button, and I bet under that is the E button, maybe. But you have an E button somewhere on your calculator. So you could do E caret 3, and the caret is the exponent button. And by the way, if you had to do it over here, E to the 1/3, if you did E, oops, looks like I don't know what that is. E caret 1/3, what you just did was e to the 1st divided by 3, because your calculator knows the rules of algebra, and it says exponents always come first. So it looks here and say, there's my exponent. Okay, e to the 1st, and then I do divide by 3. You don't want to do that. You want to do e caret parentheses 1/3. And now your calculator says, okay, I'm doing exponentials. I do the next thing I see. Oh, I see this thing in parentheses. I got to do it all. And this will give you that. Very important. Whenever you have a fraction as an exponent, you got to put it in parentheses on your calculator or you're going to get the wrong number. Okay? So e cubed is just some number. I don't know what it is. It's around 26 or something like that. 25, I don't know. So you could plot points and you can make this curve very accurately, right? But we just want to get the general shape. Is it growth or is it decay? And what's that point right there? That's all we care about when we're sketching these curves, okay? Okay, so let's look at, is that the right one? Okay, so let's look at these examples here. Boop, 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 boop. Okay, so let's see, this is growth. This is decay, because I'm looking at what happens out here. This is growth. And this is decay, because it's slowly decaying down to 0. So if this is f of x equals b to the kx, I'm going to ignore the coefficient a for now. So this is an example of k greater than 0 and b greater than 1. So you have a positive number here, and a is bigger than 1. Over here, this is an example of k less than 0 and b greater than 1. So you're still doing a number bigger than 1 in here, but k is negative. So that would be an example. This would be an example of 2 to the 3x, right? This would be an example of b is positive, but k is negative. Okay? Over here, decay again, this is an example where k is less than 0 and b is less than 1. So this would be 1/3 to the minus 3x. How can this be decay? Did I do that right? Yeah, so I don't think I did that right. Nope, I didn't do that right. So this would be b less than 1, really between 0 and 1, because we're not going to do negative values there. So this would be, I got to think. Let me pause for a minute here. Okay. So this is an example of k greater than 0, the coefficient, b less than 1. So this is an example of f of x equals b is less than 0. I can't do less than 1, I mean, sorry. So this is 1/3 raised, k is positive, 3x. Because I'm going to rewrite this as 3 to the minus 1 raised to the 3x. And what do you do when you raise an exponent to an exponent? I'm going to write this as 3 to the minus 3x. And now it looks like this one over here. Okay? So, and I guess I should have used a 2 so they were the same, but whatever. So this is a fraction raised to a positive exponent. Whenever you raise a fraction to a positive exponent, you're always going to get smaller, and it's going to cause decay. And lastly, this one is k less than 0, b less than 1. And these should have been 1s. I'm sorry. Right? We're not going to have, we're only talking about b greater than 0, greater than 1 or less than 1. We're never going to have b, this number in here, be negative. Because let me show you what happens. If you have minus 2 to the x, let's make a table of values. X, here's f of x. So if I put in 1, 2 to the first power is negative 2. If I put in 2, negative 2 squared is positive 4. So it jumps from negative to positive. Holy crap. And we put in 3, negative 2 cubed. That's an odd exponent, so the negative survives, and it's going to be negative 8. This is not a continuous function because it jumps all around. So we're never going to do this with a negative number inside the function, okay? Never going to happen. So that's why this should have been greater than 1 and greater than 1 and less than 1 and less than 1. So this is an example. F of x is equal to b is less than 1, k is negative. There we go. And like I mentioned before, I'm going to write this as 2 to the minus 1 raised to the negative 3x. Exponent raised to the exponent, I multiply and I get 2 to the plus 3x. So it's growth, okay? So these are conditions you want to keep track of for exponential decay and growth with my messy ones there. Okay? That's what you want to keep track of for these. These are 4 situations that can cause exponential decay or exponential growth. And you're going to be expected to look at a function and answer, is it decay or growth? And so you'll have to figure out how to do that. Okay? Let's try a little example problem. Though I find these to be pretty easy. 1/3 times 2/5 to the minus 3x. Is this exponential decay or growth? Well, let's see. This is a times b to the kx. B is, I don't really care about a. B is 2/5, that's less than 1. K is greater than 1. Or K is negative. So what situation was that? When you raise an exponent, a fraction that's less than 1, you raise it to an exponent, it gets smaller, but the negative sign is going to make it get bigger and go the other way. So I think this one is going to be growth. Let's see. 1/3, I got to write that down. 1/3 times 2/5 to the minus 3x. So let's go to my little friend. Symbolab, and we'll graphing, and we're going to do 1/3. So I put in parentheses 1/3 so I don't get it mixed up. And I'm going to add another set of parentheses. And I'm going to write 2/5. And then I'm going to raise it to an exponent. And the exponent has to be in parentheses. So the function knows, use all of it. Minus 3x. Okay, oh, there it is. And what do we see? We see exponential growth. And look at how fast it takes off. It goes, because it's 3x. 3x makes it fast. And so Oops. And you can see when you get, I can't even see where it is. It's so fast and it's so steep that, so when it gets to 5, 2, 3, 4, 5. So 2, this function has a value, it looks like, of 30. So, man, it grows fast. This is why exponential growth is talked about as really quick growth. This was the problem with COVID-19, is that the number of cases were growing exponentially, which meant that you had a lot of cases growing and they were getting more and more and more and more. Okay. So that's all there is to section 3.1. And there's some homework problems. And when you come to the, stop that, when you come to office hours, you could get help on the homework before the quiz so that you won't have any troubles there. So I encourage you to ask questions. I'm not going to do all the homework problems during office hours. I'm going to answer your questions on homework. So please come prepared with questions because you've tried some of the homework and you have difficulty with them and you need help. Okay? I'll see you then. Bye.